Welcome to a journey beyond the familiar, a journey into the depths of space and time. Tonight, we'll explore the vastness of the universe, starting with something that seems simple, its size. But by the end, you'll grasp something far more profound. The universe is far bigger and far stranger than we ever imagined. We begin with something most of us can easily picture: Earth. Our planet, a small speck in the grand scale of the universe, measures about 12,742 kilometers in diameter. In the grand scheme of the cosmos, Earth is tiny, but to us, it is the entire world. It's big enough that if you wanted to walk around it taking 8 hours a day at a steady pace, you'd need more than a year to finish your journey. That journey at highway speeds would still take about 2 weeks. Yet we often forget that Earth, despite its vastness, is merely a small part of something far greater. It's easy to think of Earth as our universe. After all, it is where life exists. But that's only the beginning. Our Earth is not alone. It orbits a star, the Sun, so large that 1.3 million Earths could fit inside it. At 1.39 million kilometers across, the Sun dwarfs our tiny world by a staggering 109 times. When you see the Sun, you're seeing just a small piece of the much grander story of space. And our Sun, massive as it may be, is only one star among hundreds of billions within the Milky Way galaxy. As we zoom out, the distances between planets within our solar system become incomprehensible. From Earth to the Sun, it's about 150 million kilometers, an astronomical unit, or AU, which light takes a mere 8 minutes and 20 seconds to travel. But light travels much longer to reach more distant planets. For example, light from the Sun takes about 43 minutes to reach Jupiter and 4 hours to reach Neptune. Yet these planets are not the end of our solar system. The Oort cloud, a vast spherical shell of icy objects, extends far beyond Neptune, potentially stretching up to 100,000 HUO from the Sun, almost halfway to the nearest star, Proxima Centauri, which sits over 4 light-years away. Now imagine shrinking our solar system into a scale model. If the Sun were reduced to the size of a basketball, just 24 centimeters across, Earth would be a tiny bead, only 2 mm in diameter, and it would sit 26 meters away. To place the nearest star, Proxima Centauri, in this model, you would have to travel 7,000 kilometers. That's the real emptiness of space. The closest stars are separated by vast stretches of nothingness, and our Sun is only one among hundreds of billions in a galaxy that measures 100,000 light-years across. The Milky Way, where we live, is a barred spiral galaxy with hundreds of billions of stars. It's spinning at incredible speeds, with our Sun orbiting the center of the galaxy at 828,000 kilometers per h. Even at this staggering speed, it takes 225 million years to complete one orbit. In the vast history of the universe, the position we occupy now in the galaxy was once home to dinosaurs, halfway between the arms of the spiral. But the Milky Way is not alone. It sits as a member of a cosmic community. It belongs to the local group, a small cluster of galaxies. This collection includes about 50 galaxies, although most of them are small dwarf galaxies. The 3 largest members of this group are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Andromeda, the largest, contains around 1 trillion stars and measures a staggering 220,000 light-years across. The distance between the Milky Way and Andromeda is about 2.5 million light-years. This means that light traveling at a speed of 300,000 kilometers per second would take 2.5 million years to traverse this distance. If you could somehow travel at the speed of light, which is of course impossible, the journey would still take 2.5 million years. Imagine then the size of the universe on a larger scale. The entire local group spans a mere 10 million light-years, a small region in the grand scheme of the universe. Yet even within this small group, distances are so vast that they are nearly incomprehensible to us. The Milky Way and Andromeda are gravitationally bound to each other, and in about 4 billion years they will collide and merge, forming a new galaxy. a giant elliptical galaxy that scientists have humorously dubbed Milkomeda or Milkdromeda. This collision will radically alter the night sky, with Andromeda eventually growing larger and larger, eventually filling up most of the visible sky. But even this merging of galaxies is nothing compared to what lies beyond. The Milky Way is a part of something much larger, a supercluster of galaxies. Our galaxy resides within a cluster called the Virgo cluster, which is itself part of an even larger structure called the Laniakea supercluster. Laniakea, a name derived from the Hawaiian language meaning immeasurable heaven, contains roughly 100,000 galaxies spread across 520 million light-years of space. To put this in perspective, imagine the Milky Way as a dinner plate 18 millimeters across. Laniakea, on this same scale, would be about 94 meters long, roughly the length of a football field. Laniakea is not just a random collection of galaxies, but rather a vast interconnected structure. The galaxies within Laniakea are moving through space along vast cosmic filaments and sheets, each one being pulled toward a central gravitational anomaly called the Great Attractor. This force is pulling galaxies toward it at speeds of 600 kilometers per second. The Great Attractor remains elusive, hidden behind the dense plane of our own galaxy, making it difficult for scientists to fully understand its nature. What is it? We can only speculate. Some theorize it might be a massive concentration of dark matter, or perhaps a large cluster of galaxies, but we cannot say for certain yet. When we look at this immense structure, it's clear that the universe is not uniformly spread out. It's organized into vast sheets and filaments of galaxies, forming a cosmic web. And even beyond Laniakea, there are millions of other superclusters stretching across the observable universe. Each of these superclusters contains galaxies and galaxy clusters, all linked by gravity into one unified structure. But it doesn't stop there. Beyond the superclusters, there are even larger structures, such as the Sloan Great Wall. This gigantic filament of galaxies stretches across 1.37 billion light-years, making it one of the largest known structures in the universe. It is located about 1 billion light-years away from Earth. The Sloan Great Wall is just one of many such structures that have been discovered, pointing to the existence of vast cosmic webs that extend throughout the universe. And yet, despite the incredible enormity of these structures, the universe itself is far from uniform. Between these colossal filaments of galaxies lie vast voids, enormous regions of space where galaxies are scarce. The Boötes void, discovered in 1981, is one of the largest such voids, measuring about 330 million light-years in diameter. It contains only about 60 galaxies compared to the 2,000 galaxies you would expect to find in such a vast region. This void, as massive as it is almost empty, an eerie emptiness in the cosmic landscape. Imagine standing at the center of this void, with no galaxies visible in any direction, just an ocean of nothingness stretching far beyond what we can comprehend. These voids are not merely spaces of emptiness, but they are significant in understanding the overall structure of the universe. The cosmic web, which consists of filaments of galaxies surrounding vast voids, reveals the true scale of the universe. It's a complex and intricate design that has been sculpted over billions of years by the force of gravity. And even within these voids, there are dark matter and gas, structures invisible to us but essential to the architecture of the cosmos. The universe is filled with structures we can only begin to understand. And yet, the majority of what exists in the universe remains hidden from our eyes. We have only scratched the surface of what is out there, and our ability to perceive and measure these vast distances is still in its infancy. But as our technology advances, we continue to uncover more and more of the universe's immense scale. In future parts of this story, we will zoom out even further, revealing galaxies, superclusters, and phenomena that stretch the limits of our imagination. We've ventured far from Earth, past the boundaries of our solar system, and observed the vastness of the Milky Way. But the scale of the universe still eludes our comprehension. We know the Milky Way is just one galaxy among hundreds of billions in the universe, but what does that really mean? To understand our place in this cosmic expanse, we need to go further. Let's zoom out even further and explore the relationship between the Milky Way and the larger structures of the universe, beginning with the galactic clusters. The Milky Way, with its hundreds of billions of stars, is part of a group of galaxies known as the local group. This is a small collection of about 50 galaxies, though most of them are dwarf galaxies. The three giants of the local group are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Among these, Andromeda is the largest, containing about 1 trillion stars. It stretches about 220,000 light-years across, which is more than twice the diameter of our own galaxy. The distance between the Milky Way and Andromeda is approximately 2.5 million light-years. To truly grasp the scale of this distance, imagine a scenario where you could travel at the speed of light. Even at that unimaginable speed, the journey would take 2.5 million years. And remember, this is the closest major galaxy to us. In fact, most galaxies in the universe are much farther away. As we step further into this story, we need to understand that these galaxies are not stationary. They are all in motion, driven by the gravitational forces of the structures they are part of. The Milky Way and Andromeda are not just distant neighbors, they are on a collision course. In about 4 billion years, these two galaxies will collide and merge, creating a massive elliptical galaxy. During this galactic merger, the night sky will change dramatically. Andromeda will grow larger and larger in the sky until it completely dominates the view, transforming from a faint smudge to a giant swirling spiral in our skies. The collision will ignite waves of new star formation as the gas clouds of both galaxies collide and compress, creating brilliant new stars. However, don't expect the stars themselves to collide. The distances between stars are so vast that it's unlikely any two stars will ever come close enough to interact. The most noticeable effect will be the gravitational disruption of orbits. The stars in both galaxies will be scattered, their paths altered as they are drawn into new orbits around the merged galaxy's center. Triangulum, the third largest member of the local group, is a smaller galaxy with around 40 billion stars. It is likely gravitationally bound to Andromeda, and during the Andromeda-Milky Way merger, Triangulum may be drawn into the collision as well. This will create an even more complex cosmic interaction, with stars from all three galaxies mixing together. But even the local group, with its 50 galaxies, is just a small fraction of the larger cosmic structure. The local group is part of the Laniakea supercluster, a vast sprawling structure that contains about 100,000 galaxies spread over a region of space about 520 million light-years in diameter. To help grasp the scale, if the Milky Way were the size of a dinner plate, Laniakea would stretch across the length of a football field, with its galaxies arranged in a web-like structure. This supercluster is not a random collection of galaxies. It is a coherent structure held together by gravity. The galaxies within Laniakea are flowing through space along vast filaments and sheets, and at the center of this cosmic flow lies a mysterious region known as the Great Attractor. The Great Attractor is a gravitational anomaly that is pulling galaxies, including our own Milky Way, toward it at speeds of up to 600 kilometers per second. Yet, despite its massive influence, the Great Attractor remains largely invisible to us. It's hidden behind the dense plane of our own galaxy, obscured by the stars, gas, and dust in the Milky Way. Its exact nature remains a mystery. Some scientists speculate that it could be a concentration of dark matter, while others propose that it might be a massive cluster of galaxies that are too distant for us to observe directly. The existence of the Great Attractor reveals just how dynamic and interconnected the universe is. Galaxies are not static entities. They are in constant motion, influenced by the gravity of other galaxies and larger structures, like superclusters. And this gravitational flow doesn't stop at the Great Attractor. It's just one part of an even larger structure called the Shapley supercluster. The Shapley supercluster is one of the largest known concentrations of matter in the nearby universe. Located about 650 million light-years away, it contains over 8,000 galaxies. This immense cluster is one of the most massive gravitational objects in the universe. And as we zoom out even further, we start to realize that the universe is not only a series of isolated galaxies and superclusters, but a vast interconnected cosmic web. This web is filled with immense structures, like the Sloan Great Wall, which stretches a staggering 1.37 billion light-years across. The Sloan Great Wall is a massive filament of galaxies, creating a cosmic thread that stretches across more than 1% of the observable universe's diameter. This wall is just one example of the vast, interconnected structures that span the universe. But these structures are not evenly distributed. Between these massive filaments, there are enormous voids, vast regions of space that are nearly empty of galaxies. One of the largest of these voids is the Boötis void, which spans about 330 million light-years. Inside this void, there are only about 60 galaxies, compared to the 2,000 galaxies you might expect to find in such a region. If you could somehow find yourself in the center of the Boötis void, the night sky would be nearly empty, with only faint glows from distant galaxies at the edges of the void. But even the voids are not truly empty. They are filled with dark matter, an invisible substance that we cannot directly observe, but whose existence we know through its gravitational effects. Dark matter makes up about 27% of the total mass and energy of the universe. Without it, galaxies would not have formed the way they did. The force of gravity from dark matter is what helped to collapse the first clouds of gas and dust into the galaxies we see today. The Milky Way is surrounded by a dark matter halo, which extends far beyond the visible stars of the galaxy. In fact, the mass of dark matter in this halo is thought to be several times greater than the mass of all the stars and gas in the Milky Way combined. This is the invisible scaffolding that holds the galaxy together and keeps it intact, despite the chaotic motions of the stars and other matter within it. But dark matter is just one part of the puzzle. There is another, even more mysterious component to the universe that makes up the majority of its mass energy content: dark energy. Dark energy is a repulsive force that is driving the accelerated expansion of the universe. It makes up about 68% of the total energy density of the universe. Dark energy is responsible for the fact that galaxies are moving away from us faster and faster, and that the expansion of the universe is speeding up over time. Despite our understanding of dark matter and dark energy, we still have very little idea what they actually are. We can observe their effects on the universe, but we have yet to detect them directly. These two components make up more than 95% of the universe, leaving only a small fraction of ordinary matter, what we can see and touch. The rest, the overwhelming majority of the universe, is invisible to us. It remains a mystery, one we continue to explore as we look further into the cosmos. We've already explored the vastness of our galaxy and the neighboring galaxies of the local group, as well as the enormous structures that define our cosmic environment. But even that is only the beginning of our journey across the universe. Now, let's zoom out even further, from superclusters and galactic walls to the larger cosmic web that connects the universe's largest structures. The more we expand our vision, the more we see how connected and interconnected everything truly is. This is where the universe begins to take on a new shape, an intricate, sprawling web of galaxies, clusters, and voids. The universe, it turns out, is not just a scattered collection of galaxies, but a vast, interconnected network that stretches across billions of light years. This structure is often called the cosmic web. It consists of massive threads or filaments of galaxies, clusters of galaxies, and dark matter, forming an intricate pattern of vast cosmic structures stretching through the universe. These threads of galaxies are interconnected, forming enormous walls of matter, separated by giant voids, regions where very few galaxies reside. To understand the cosmic web, imagine this. In the early universe, matter was spread out relatively evenly, but small, slight variations in density, perhaps as small as 1 part in 100,000, led to gravitational instability. The regions with slightly higher density had slightly stronger gravity, which pulled in more matter, increasing their density further. This process, known as gravitational collapse, slowly shaped the universe into the structure we observe today. Over billions of years, the gravitational pull of dark matter amplified the effect, pulling matter together into these massive galactic filaments. The Sloan Great Wall is one of the most impressive and well-known examples of this cosmic web. This gigantic structure is a filament of galaxies that stretches across a mind-boggling 1.37 billion light-years. If you think back to the unimaginable size of the Milky Way, with its 100,000 light-years across, you can begin to grasp how enormous this structure really is. The Sloan Great Wall is just one of the many supergalactic filaments that stretch across the universe, all connected by invisible strands of dark matter. These galactic filaments are part of even larger structures known as superclusters. We've already mentioned Laniakea, the supercluster that includes our own Milky Way, but it's not the only supercluster. There are hundreds of thousands of them scattered across the universe, forming an intricate network of interconnected galaxy clusters. The Shapley supercluster, for example, is one of the largest known structures in the universe, located about 650 million light-years away. It contains more than 8,000 galaxies. This supercluster is one of the largest concentrations of matter in the nearby universe, and like Laniakea, it is held together by the gravitational force of dark matter. What's fascinating about these superclusters is not just their sheer size, but their motion through space. The galaxies within these superclusters are not static, they are all moving. Galaxies are flowing through the cosmic web along the paths carved by gravity, converging toward areas of higher density. One of the most intriguing aspects of this movement is the presence of the Great Attractor, a region of space that is pulling galaxies, including our own, toward it at incredible speeds. The Great Attractor, despite its immense gravitational influence, remains hidden behind the plane of the Milky Way, obscured by stars, gas, and dust. We can't observe it directly, but we know it exists by the way galaxies move toward it. While these galactic movements and superclusters seem to be ordered, the universe is still mostly empty. Between these filaments and clusters, there are vast, seemingly empty spaces, voids. These voids are not completely empty, of course, but they are far less dense than typical regions of space. The Boötis void, for example, is a massive, spherical region spanning about 330 million light-years, containing far fewer galaxies than one might expect. If you were somehow placed in the center of this void, you would be surrounded by a nearly empty space. Even with a powerful telescope, you would see very few galaxies, and the night sky would appear incredibly dark. It's a sobering reminder of how much of the universe is composed of vast stretches of emptiness. These voids and walls of galaxies form the cosmic foam, the largest scale structure of the universe, a web-like framework that defines the universe's organization. The web connects galaxies in thin strands and sheets, creating a pattern of matter that stretches over the entire observable universe. It's like a giant invisible latticework stretching through the cosmos. This structure formed as the universe cooled and expanded, guided by the invisible hand of gravity. While these structures are awe-inspiring, the story of the universe doesn't stop with the cosmic web. As we step back even further, we start to see the limits of our observable universe. We live in what astronomers call the observable universe, which is defined by the distance that light has been able to travel since the Big Bang. However, because the universe has been expanding since the Big Bang, the observable universe extends far beyond what we would expect based on the age of the universe alone. In fact, the observable universe has a radius of about 46.5 billion light-years, which is nearly double the age of the universe itself. This is because the universe has been expanding at an accelerating rate, and distant galaxies are now moving away from us faster than light can travel toward us. This means that there are regions of space that we can never observe, no matter how advanced our technology becomes. These unreachable regions are beyond the cosmic horizon, a boundary that defines the furthest point we can ever see. What's more, we now know that the observable universe contains roughly 2 trillion galaxies. That's not a typo. 2 trillion galaxies. Each of those galaxies contains billions, if not hundreds of billions of stars. But this staggering number still represents only a fraction of the universe. Beyond the observable universe lies more space, more galaxies, more stars, possibly an infinite number. The universe we can see and measure is just a small slice of what might be out there. The true size of the universe is still a subject of debate and research. Is the universe infinite? It might be. Some theories suggest that the universe could be infinite in size, with no boundaries or edges. If the universe is indeed infinite, then that means there could be an infinite number of galaxies and stars, each of them stretching infinitely in all directions. The idea of infinity is mind-boggling, and even though we can do the math and study the models, it's difficult for us to truly understand what that means. And if the universe is infinite, then what does that mean for life? In an infinite universe, anything that can happen does happen somewhere. There could be infinite versions of Earth, infinite copies of you, all scattered across the vast expanse of space. Some of these versions might be identical to us, while others might differ in ways we can't even imagine. This is one of the strange implications of infinity, a concept that challenges both our scientific understanding and our philosophical beliefs. Yet, despite these mind-bending thoughts, the universe is still something we can study. The scientific methods we have at our disposal allow us to observe, measure, and understand parts of the universe that are mind-bogglingly distant. The further we look, the more we see galaxies, stars, and structures that were once beyond our wildest imaginations. But with every discovery, we are reminded that there is so much more out there, more that we can't observe, more that we can't even comprehend. We've come a long way from seeing only a few thousand stars in the night sky, to mapping entire galaxies and superclusters. But the universe is so vast, so complex, that it will always remain a mystery in many ways. As we continue our journey through this cosmic tapestry, we will continue to explore the edges of the observable universe, charting new discoveries and expanding our understanding. But no matter how much we learn, we are always reminded that the universe is much larger than we could ever truly fathom, and that there is always more to discover, explore, and understand.
The mystery of the cosmos will remain, and that is part of what makes it so endlessly fascinating.
The universe, vast beyond comprehension, is not just made up of the visible matter we can observe. Even as we begin to grasp the scale of space and time, we encounter two deeply perplexing and invisible forces that dominate the cosmos: dark matter and dark energy. Together, they make up around 95% of the total content of the universe. But despite their overwhelming presence, we have yet to directly observe or fully understand them. Dark matter is a critical component of the universe's structure. It makes up about 27% of the universe's total mass energy content. However, it doesn't emit, absorb, or reflect light, making it invisible to our instruments. Despite this, we know it exists because of its gravitational effects on visible matter. Without dark matter, galaxies and clusters of galaxies would be unstable, flying apart rather than remaining intact. The stars in galaxies move at such high speeds that, without an invisible additional force, they would not stay bound by gravity. This additional force is provided by dark matter, whose presence we can only detect through the way it influences the movement of stars and galaxies. Scientists have yet to directly detect dark matter. Though numerous experiments and detectors have been built to search for dark matter particles, nothing definitive has yet been found. The leading candidates for dark matter are weakly interacting massive particles, WIMPs, which would have mass and interact only via gravity and possibly the weak nuclear force, but they would not interact with light in any way. Despite decades of research and experiments designed to detect these elusive particles, dark matter continues to remain one of the universe's most profound mysteries. It is likely that dark matter is a form of matter that interacts so weakly with normal matter that it passes right through us, through Earth, and through everything around us without any noticeable interaction. Still, we can't deny its existence because of its gravitational influence, which plays a significant role in the structure of the universe. Now, dark energy is the more mysterious force between the two. It accounts for about 68% of the total energy content of the universe, and it is responsible for the accelerating expansion of the cosmos. This was a shocking discovery made in 1998 when astronomers studying distant supernovae found that not only was the universe expanding, but the rate of that expansion was speeding up over time. This discovery defied everything that scientists had previously believed. For decades, it was thought that the gravitational pull of all the matter in the universe would slow down the expansion. Instead, dark energy is driving the expansion at an ever-accelerating rate, causing galaxies to move farther apart with increasing speed. The nature of dark energy remains elusive. Scientists hypothesize that it could be a fundamental property of space itself. As space expands, dark energy becomes more pronounced, causing the expansion to accelerate. However, the exact mechanism behind dark energy remains unclear. Its effects can be measured, and its influence on the universe's expansion is undeniable, but its true nature remains one of the greatest unsolved problems in cosmology. Whether dark energy is a manifestation of some new type of energy or an intrinsic property of space is still up for debate, but its effects on the universe are clear. When we consider the ultimate fate of the universe, both dark matter and dark energy play crucial roles. The universe is on a trajectory that could end in one of two ways, both determined by the interplay of these forces. The first possible end is the heat death of the universe. In this scenario, the expansion of the universe continues at an accelerating rate, causing galaxies to drift further apart. As stars burn out and the gas necessary for star formation is exhausted, the universe will grow darker and colder. Eventually, the temperature will approach absolute zero, and the universe will reach a state of maximum entropy, where all matter and energy are evenly distributed and no thermodynamic work can be done. This cold, lifeless state would be the end of everything. Even black holes would eventually evaporate, leaving nothing but an expanse of empty space. The second possible fate of the universe is the Big Rip, a much more dramatic scenario that depends on how dark energy behaves in the future. If dark energy grows stronger over time, it could eventually overcome the gravitational pull that holds galaxies, stars, planets, and even atoms together. In this case, the expansion of the universe would accelerate to the point where the fabric of space itself tears apart, ripping apart galaxies, stars, and even atoms. This violent scenario would mark the final dissolution of all matter in the universe. Though both scenarios present grim futures for the universe, they are far off in time. These events will not occur for many trillions of years, but they serve as a reminder of the ultimate fate that awaits the cosmos. The scale of time is just as staggering as the scale of space. The universe is 13.8 billion years old, but it will continue to evolve for trillions of years more. As dark energy continues to drive the accelerated expansion, and as stars burn out, the universe will gradually approach a state where life, matter, and structure cease to exist. Even so, these processes unfold over timescales that stretch far beyond the human experience, making it almost impossible for us to truly grasp what such a future would entail. Understanding these cosmic forces and their implications provides us with a humbling perspective. The universe operates on a scale of both space and time that transcends human comprehension. And yet, in the brief moment that we occupy, we have developed the ability to study and measure the universe, to see beyond our small corner of existence and peer into the vastness of space and time. It is this ability to understand our place in such a grand cosmos that defines us as a species. The universe, filled with its unseen forces and vast stretches of empty space, is not merely a collection of stars and galaxies. It is a dynamic, ever-evolving system where the forces of dark matter and dark energy shape the destiny of all things. We live in a universe defined by these forces, forces that control the future of all matter, stars, galaxies, and the very fabric of space-time itself. Yet, even as we learn more about these cosmic forces, we are confronted with the humbling realization that there is still so much more to understand. The scale of the universe and the unknown forces that shape it serves as a reminder of just how vast, mysterious, and complex the cosmos truly is. The concept of time in the universe is as mind-boggling as the scale of space. When we study the universe, we don't just encounter vast distances, but also the stretching and warping of time itself. Time behaves differently at different scales. What seems like an eternity to humans might be nothing more than a brief instant in the grand timeline of the cosmos. We are familiar with the passage of time in our daily lives. We wake up, go to work, and sleep, each day lasting 24 hours. But the universe operates on an entirely different time scale. Stars live and die over the course of millions to billions of years. Galaxies evolve over even longer periods. The universe itself, born 13.8 billion years ago in the Big Bang, has a timeline that stretches into the unimaginable future, and we are only witnessing a fleeting moment in its story. The birth of the universe itself is a moment that we can trace back to the Big Bang. Before the Big Bang, there was nothing, no matter, no energy, no space, and no time. Then, in an instant, everything began. The universe expanded rapidly in a process called inflation. Within a fraction of a second, it went from being smaller than an atom to a size larger than a galaxy. During this moment of inflation, the universe cooled and began to form the first elementary particles. This rapid expansion set the stage for everything that followed: stars, galaxies, and ultimately, life. The early universe was a hot, dense place. For the first 380,000 years, the universe was filled with a hot plasma of protons, neutrons, and electrons. Photons, the particles of light, were constantly being scattered by these particles, making it impossible for light to travel freely. The universe was opaque, but as it continued to expand and cool, electrons and protons combined to form hydrogen atoms. This moment, known as recombination, allowed light to finally travel through space, marking the beginning of the transparent universe we observe today. The faint glow from this era, known as the cosmic microwave background radiation, CMB, is still detectable today and provides us with a snapshot of the early universe when it was just 380,000 years old. This is one of the oldest and most important pieces of evidence we have for the universe's beginnings. After recombination, the universe entered a period known as the Dark Ages. During this time, there were no stars or galaxies. The universe was dark, filled only with hydrogen and helium gas. But gravity was slowly pulling this gas together, and over the next few 100 million years, the first stars began to form. These stars were massive, burning incredibly hot and bright, but their lives were short. They lived only a few million years before exploding as supernovae, scattering the heavier elements necessary for the formation of planets and life. The formation of the first galaxies followed soon after, and from these early galaxies, the complex structures we see today began to evolve. One of the most important discoveries in understanding the universe's time is the observation that the universe is expanding. This was first confirmed by Edwin Hubble in the 1920s, when he observed that galaxies were moving away from us in all directions. The further a galaxy is, the faster it is moving away. This discovery led to the realization that the universe must have been much smaller in the past, and if we trace the expansion backward in time, we arrive at the Big Bang. The expansion of the universe is not only confirmed by the observation of galaxies moving away from us, but also by the cosmic microwave background radiation. This ancient radiation is a remnant from the early universe, and its study has provided us with crucial information about the universe's age and composition. The CMB is a snapshot of the universe when it was only 380,000 years old. By studying this radiation, scientists have been able to measure the age of the universe and its rate of expansion. As the universe expanded, the density of matter decreased. Stars and galaxies formed as gravity pulled matter together. But the universe was still a very different place from what we know today. The first galaxies were small and irregular, not the spirals or elliptical galaxies we see now. Over billions of years, these galaxies merged, grew, and formed the structures we observe today. The Milky Way, our galaxy, formed from these early structures. Our solar system, which formed about 4.6 billion years ago, is a relatively young part of this cosmic history. While the universe has existed for over 13.8 billion years, the Earth itself is a mere speck in this grand timeline. Our Sun, a relatively young star, is expected to live for around 10 billion years in total. It's about halfway through its life, and in about 5 billion years, it will exhaust the hydrogen in its core and begin to expand into a red giant. This process will cause the outer layers of the Sun to expand and engulf the inner planets, possibly including Earth. After that, the Sun will shed its outer layers, leaving behind a white dwarf, a small, dense remnant that will slowly cool over billions of years. But the Sun is not the only star in the universe. The Milky Way, our galaxy, contains hundreds of billions of stars, and the universe is filled with countless galaxies. These galaxies are not static, they are constantly evolving. Some galaxies collide and merge, forming larger galaxies. The future of our galaxy, the Milky Way, is tied to its collision with the Andromeda galaxy. In about 4 billion years, Andromeda and the Milky Way will collide, eventually merging to form a new elliptical galaxy. While the individual stars in these galaxies are so far apart that collisions between them are unlikely, the gravitational interactions will cause massive changes. Our Sun and other stars may be thrown into new orbits, and the night sky will be dramatically different. Time in the universe is not just a linear progression from the past to the future. It is also shaped by the interactions of matter and energy. The scale of time in the universe is incredibly vast, with events unfolding over millions and billions of years. As we look back in time, we see galaxies and stars that have long since passed their prime, their light traveling across vast stretches of space to reach us. Some of the light we see tonight left its source millions or even billions of years ago. The further we look, the further back in time we are seeing. In this sense, the universe is a time machine, constantly sending us signals from the past. In a way, the universe itself is in a constant state of evolution, expanding outward and growing colder and darker as time moves forward. The stars will burn out, galaxies will collide, and the universe will continue to evolve, driven by the forces of gravity, dark matter. The future is uncertain, but one thing is clear: the universe will continue to change, and we are witnessing just one small chapter in its long history. The vastness of the universe and the long timeline it spans are awe-inspiring. The more we learn about the cosmos, the more we realize how much we still don't know. Every discovery brings with it new questions, and the more we understand, the more we uncover about the universe's complexities. As we continue to explore, we are reminded of the immense scale of time and space, how small we are in comparison to the vast expanse of the universe, yet how remarkable it is that we are here at all, able to comprehend these cosmic wonders. Now that we've established the vast timeline of the universe, it's time to shift our focus to one of the most fascinating aspects of cosmic evolution: the large-scale structure of the universe itself. As we look further out into the cosmos, we begin to see patterns, structures that span millions, even billions of light years. These structures aren't randomly scattered. They form a kind of cosmic web, with galaxies arranged in intricate patterns of filaments and clusters, surrounding vast voids of empty space. This is the large-scale structure of the universe, and it's a result of the fundamental force of gravity shaping matter across the cosmos. The first piece of this cosmic puzzle is the formation of galaxies. Galaxies, the building blocks of the universe, are massive collections of stars, gas, dust, and dark matter, all bound together by gravity. The Milky Way, our galaxy, is just one of about 2 trillion galaxies in the observable universe. The process by which galaxies form, grow, and evolve is a fundamental aspect of cosmic history, and understanding it gives us insights into the history and future of the universe itself. It all began with tiny variations in the distribution of matter in the early universe. Shortly after the Big Bang, matter was almost evenly spread out, but small fluctuations, tiny differences in density, began to occur. These fluctuations were the seeds from which galaxies would eventually form. Over millions of years, regions with slightly higher density began to attract more matter, growing denser as gravity pulled more gas and dust toward them. The formation of the first stars and galaxies began, sparking a cascade of events that would shape the structure of the universe as we know it. The universe's evolution is marked by a series of cosmic milestones, from the first stars, known as population 3 stars, to the birth of the first galaxies. Gravity worked tirelessly, pulling matter into larger and larger clumps. As galaxies formed, some began to merge and grow, while others remained isolated. Eventually, these galaxies grouped together into galaxy clusters, large collections of galaxies bound by gravity. These clusters are not evenly spaced, however. They are connected by vast cosmic filaments, long strands of galaxies that stretch across the universe, creating a web-like structure. One of the most remarkable aspects of the large-scale structure of the universe is the discovery of the cosmic web. This web is composed of clusters of galaxies, each connected by vast filaments of dark matter and gas. Between these filaments lie enormous voids, regions of space where galaxies are almost completely absent. These voids can span hundreds of millions of light years across and are some of the most empty and desolate places in the cosmos. Understanding the cosmic web has allowed scientists to map the large-scale distribution of galaxies and uncover the forces that have shaped the universe over billions of years. But the story of the universe's structure doesn't end with galaxies and clusters. In fact, the largest structures in the universe are vast superclusters, groups of galaxy clusters bound together by gravity. Our galaxy, the Milky Way, is part of a relatively small supercluster called the Laniakea supercluster, which contains about 100,000 galaxies spread over a region 520 million light-years across. Laniakea is not just a random collection of galaxies, it is a coherent structure that is moving through space, drawn toward a mysterious region of space called the Great Attractor. The Great Attractor is a gravitational anomaly that exerts an enormous pull on our supercluster, as well as several others in the nearby universe. Its exact nature remains unknown, but it is believed to be a massive concentration of matter, possibly dark matter, that is pulling entire superclusters toward it. As we zoom out even further, the scale of the universe continues to expand. Laniakea is just one supercluster in a vast network of superclusters spread across the observable universe. These superclusters are connected by massive cosmic filaments, the largest structures in the universe. One of the most well-known and studied of these is the Sloan Great Wall, a massive filament of galaxies that stretches across more than 1.3 billion light-years. These structures are so large that they challenge our understanding of the universe. According to our current cosmological models, these filaments shouldn't exist. They are simply too big for gravity to have had enough time to form them. And yet, they do exist, defying expectations and forcing scientists to reconsider their models of cosmic evolution. The cosmic web is not just a collection of galaxies and clusters, it is a dynamic and evolving structure. The distribution of galaxies is not uniform. Some regions of the universe are densely packed with galaxies, while others are nearly empty. The largest galaxies are often found at the intersections of filaments, where gravity is strongest. These massive galaxies, known as supermassive galaxies, can contain trillions of stars and have a profound influence on their surrounding environment. They are thought to have played a key role in the evolution of the cosmic web, helping to shape the distribution of galaxies and clusters over time. But as we explore the vastness of the universe, we encounter something even more mysterious: dark matter. While regular matter, the stuff that makes up stars, planets, and galaxies, accounts for only about 5% of the total matter and energy in the universe, the rest is made up of dark matter and dark energy. Dark matter is invisible and undetectable by normal means, but its presence is inferred from its gravitational effects on visible matter. It forms the scaffolding of the universe, shaping the structure of galaxies and clusters. Without dark matter, galaxies wouldn't have formed in the first place. The universe would be a vastly different place. We can see the effects of dark matter in the way galaxies move. When we observe the rotation of galaxies, we notice something strange. The outer regions of galaxies spin much faster than they should, based on the visible matter we can see. If the only matter in a galaxy were the stars and gas that we observe, the galaxy would tear itself apart due to the high velocity of its outer regions. But galaxies don't fly apart. Instead, they stay intact. held together by a mysterious substance that we call dark matter. The mass of dark matter in a galaxy far exceeds the mass of its visible stars, and it is this dark matter that provides the necessary gravitational pull to keep the galaxy from flying apart. Even on the largest scales, dark matter plays a crucial role in shaping the universe. Galaxy clusters, which are collections of galaxies bound together by gravity, contain large amounts of dark matter. In fact, the mass of dark matter in a galaxy cluster is often much greater than the mass of the visible galaxies themselves. The distribution of dark matter in these clusters can be mapped by observing how light bends as it passes through the gravitational field of the dark matter. This phenomenon, called gravitational lensing, provides us with one of the few ways to observe dark matter directly. But dark matter is just one part of the cosmic puzzle. There is another mysterious force at work in the universe: dark energy. Dark energy is the name given to the mysterious force that is driving the accelerating expansion of the universe. It was first detected in the late 1990s when astronomers observed that distant galaxies were moving away from us at an accelerating rate. This discovery was shocking because it contradicted previous assumptions that gravity would slow the expansion of the universe over time. Instead, it seems that space itself is stretching, and dark energy is the force responsible for this acceleration. Dark energy is believed to make up about 68% of the total energy content of the universe. It is a fundamental force, yet we know very little about it. It doesn't seem to interact with matter in the same way that gravity or electromagnetism does. Instead, it appears to have a repulsive effect on space itself, causing the universe to expand at an ever-increasing rate. The exact nature of dark energy is one of the biggest mysteries in modern cosmology, and scientists are still trying to understand its properties and behavior. The discovery of dark energy has profound implications for the future of the universe. If the expansion of the universe continues to accelerate, it could lead to the eventual heat death of the universe. In this scenario, galaxies, stars, and even atoms would be spread out so far apart that no meaningful interactions would occur. The universe would become cold, dark, and devoid of life. This is a scenario that is difficult to imagine, but it is one that scientists believe is a possibility in the far future. As we continue to explore the universe, we are confronted with questions that challenge our understanding of reality itself. How did the universe come to be? What is dark matter and dark energy? What will the future of the universe look like? These are questions that continue to inspire us, driving us to explore further, to learn more, and to understand the vastness of the cosmos. The universe is a place of immense mystery, and the more we discover, the more we realize how much there is still to learn. As we venture further into the depths of the universe's structure, we now arrive at one of the most perplexing and awe-inspiring aspects of all that we've explored: the large voids and superclusters that span vast regions of space. The universe, though overwhelmingly populated with galaxies and stars, also contains enormous stretches of nearly empty space. These voids are some of the largest features in the universe and are essential to understanding the large-scale structure of the cosmos. Void regions, as their name implies, are areas where very few galaxies can be found. These regions of emptiness make up about 80% of the universe's volume, yet despite their vastness, they hold relatively little matter. Voids are not completely empty. There are still some sparse galaxies scattered throughout them, but they are striking in their absence of the dense clustered structures that dominate most of the observable universe. Their sheer emptiness, often extending hundreds of millions of light years across, gives us a glimpse into the large-scale dynamics of cosmic structure formation. The existence of these voids also sheds light on the gravitational forces shaping the universe. In the early days following the Big Bang, matter was fairly evenly distributed. However, slight fluctuations in density in the primordial universe were enough to kickstart the formation of the structures we see today. Over billions of years, gravity has pulled galaxies and other forms of matter together, forming filaments of galaxies that connect into vast superclusters. Where there isn't sufficient matter to clump together, the result is these enormous regions of space devoid of galaxies, voids that stretch across unimaginable distances. One of the most significant voids we know of is the Boötes void, sometimes called the Great Void, which is roughly 330 million light-years across. If you were to be placed inside it, the nearest significant concentration of galaxies would be so far away that they would appear as faint specks in the distance. The Boötis void is one of the largest and most studied voids, and it serves as a stark reminder of how much of the universe remains unfilled by matter. Though they may appear to be empty, voids are not truly void in the sense of being completely devoid of any structure. Recent studies of these voids have shown that they are filled with diffuse gas, dark matter, and even a few small galaxies scattered throughout. Yet the density of galaxies in voids is vastly lower than the average density in the rest of the universe, which gives us important insights into how matter behaves at the largest scales. The study of voids allows us to understand the nature of dark matter, the distribution of galaxies, and the forces that govern the large-scale structure of the universe. Moving outward from the voids, we encounter the monumental superclusters. Superclusters are massive structures that contain hundreds or even thousands of galaxies, gravitationally bound together. These are the largest known structures in the universe, and they contain the largest concentration of galaxies, stars, and dark matter in the cosmos. Superclusters are not uniformly distributed. They tend to form along cosmic filaments that stretch across the universe, creating a network of interconnected galaxy clusters and superclusters that form a cosmic web. The Laniakea supercluster, for instance, is our home supercluster, containing about 100,000 galaxies spread out over 520 million light-years. Laniakea is not just a random collection of galaxies, but rather a coherent structure bound together by gravity. Its galaxies, stars, and matter are all drawn toward a central point of gravitational attraction known as the Great Attractor. The Great Attractor, located about 250 million light-years away, is a region of space where the gravitational pull is so strong that entire galaxy superclusters, including Laniakea, are moving toward it at high speeds. While we have begun to understand the gravitational forces at work within superclusters, the exact nature of the Great Attractor remains one of the universe's most significant mysteries. Some scientists hypothesize that it might be a concentration of dark matter, while others suggest it could be an unseen galaxy cluster. However, since it is obscured by the dense plane of our own galaxy, the Milky Way, we can't yet observe it directly. What we do know is that it exerts a tremendous pull on the galaxies within the Laniakea supercluster and possibly even beyond, driving a continuous flow of galaxies toward it. The Laniakea supercluster is only one of millions of superclusters scattered throughout the observable universe. Some superclusters are relatively small, containing only a few dozen galaxies, while others are massive and spread over hundreds of millions of light-years. The largest supercluster currently known is the Shapley supercluster, which lies about 650 million light-years away and contains more than 8,000 galaxies. These superclusters are often connected by large cosmic filaments, which form the backbone of the cosmic web. Superclusters, filaments, and voids are not the only features that define the large-scale structure of the universe. Astronomers have also discovered a fascinating phenomenon known as the Great Wall. Great walls are vast sheets of galaxies that stretch across hundreds of millions of light-years. The Sloan Great Wall, for example, is a massive filament of galaxies that stretches more than 1.3 billion light-years. These colossal walls are so vast that they challenge our understanding of how galaxies have formed and evolved. The discovery of the Sloan Great Wall led some astronomers to question the limitations of cosmological theory. Some scientists have argued that such massive structures should not exist because the force of gravity would not have had enough time to pull matter together into such enormous configurations. Yet, despite these challenges to our understanding, the Great Wall is real. It exists. And it is not alone. The Hercules Corona Borealis Great Wall is an even larger structure that measures around 10 billion light-years across. This immense structure, if it truly exists as a single entity, would constitute one of the largest, most massive features in the observable universe. Its discovery has led scientists to rethink the very foundations of cosmic structure formation and has raised new questions about the nature of the universe itself. These vast cosmic structures, voids, superclusters, great walls, are not just scattered randomly across space. They form a web-like pattern known as the cosmic web that is created by the distribution of dark matter and the gravitational forces at work in the universe. This web-like structure is the largest scale structure in the universe and provides us with a blueprint for how the universe has evolved over time. The cosmic web is not static. It is constantly evolving, with galaxies and matter flowing along the filaments, pulled by the gravitational attraction of more massive structures. The cosmic web is also a reminder of how much of the universe is hidden from us. Dark matter, which makes up about 27% of the universe, cannot be seen directly. It does not emit, absorb, or reflect light. Yet its presence can be inferred from its gravitational effects on visible matter. Dark matter provides the scaffolding for galaxies, clusters, and superclusters to form. Without dark matter, galaxies would not have the mass to hold together, and the universe would look vastly different from what we observe today. Dark energy, the mysterious force driving the accelerating expansion of the universe, is another hidden force that shapes the large-scale structure of the cosmos. Dark energy makes up about 68% of the universe, and its presence has profound implications for the future of the universe. If dark energy continues to dominate, it will eventually lead to the heat death of the universe, a state of maximum entropy where all matter and energy are spread out evenly, and no meaningful change can occur. The study of these large-scale structures, voids, superclusters, great walls, has revolutionized our understanding of the universe. We have learned that the universe is not a homogeneous collection of stars and galaxies. Instead, it is a dynamic, ever-evolving structure shaped by the interplay of gravity, dark matter, and dark energy. These discoveries challenge our understanding of the universe and open up new avenues of exploration and inquiry. The question that remains is how we continue to study and explore these structures. The James Webb Space Telescope, set to launch in the coming years, promises to revolutionize our understanding of the universe by providing us with unprecedented views of distant galaxies and the large-scale structure of the cosmos. As we look deeper into space, we will continue to uncover new mysteries and refine our understanding of the universe's origins, structure, and eventual fate. Now, as we continue our journey through the vastness of space, we start to focus on something truly mind-boggling: the observable universe itself, and the fundamental questions about the universe's size and structure that challenge even the most advanced cosmological models. We've seen the incredible complexity of the cosmic web, the voids, the superclusters, and the great walls. But there's something even more awe-inspiring to consider: the sheer scale of the observable universe, which contains an incomprehensible number of galaxies, stars, and planets. The observable universe is defined as the region of space from which light has had enough time to reach us since the Big Bang. In other words, it's the limit of the observable universe based on the age of the universe, which is about 13.8 billion years. We might think that the observable universe would simply be 13.8 billion light-years in radius, but as we've mentioned earlier, the universe has been expanding since the Big Bang. And it's not just expanding in a simple way, the rate of expansion is accelerating. A discovery that was made in 1998, when scientists studying distant supernovae noticed that galaxies were moving away from us faster than they should, given the gravitational pull that should be slowing them down. This accelerating expansion is driven by a mysterious force called dark energy, which makes up roughly 68% of the energy density of the universe. As a result, the observable universe is much larger than we might expect. Its radius is about 46.5 billion light-years, which makes the observable universe about 93 billion light-years across. This figure is not just theoretical, it's based on current models that take into account the expansion of space itself. So if you think about it, the observable universe stretches across a vast span of time and space, far beyond the distances we can even begin to comprehend. To grasp the scale of the observable universe, consider this. Even with this 93 billion light-year diameter, we're still only seeing a fraction of what may actually exist. Our observable universe is just a tiny speck in the grander scheme of things, and what lies beyond our cosmic horizon remains a mystery. It's crucial to realize that the observable universe is not the entire universe. What we can see is constrained by the cosmic horizon, which marks the limits of how far light has traveled since the beginning of the universe. The regions of space that lie beyond that horizon will forever remain inaccessible to us, because their light simply hasn't had enough time to reach us yet. Within this vast observable universe, there are estimated to be about 2 trillion galaxies. Yes, you read that correctly. 2 trillion. When you compare that number to the 100 to 200 billion galaxies once thought to exist, it's staggering. And that's just the galaxies. Each one of those galaxies contains hundreds of billions of stars, many of which likely have planets orbiting around them. Some of these planets may even harbor life, though we have no definitive evidence of extraterrestrial life yet. The staggering number of planets alone is enough to make anyone's head spin. Based on current estimates, there could be at least 300 billion trillion planets in the observable universe, many of which are in the habitable zones of their stars, regions where conditions might allow liquid water to exist, potentially providing the right environment for life to emerge. Now, here's where it gets even more perplexing. Many of these planets may share similarities with Earth, but we still don't know how many are truly Earth-like or capable of supporting life. While we've discovered thousands of exoplanets in the past few decades, many of them are gas giants like Jupiter, and we're still in the early stages of studying whether any exoplanets have the conditions required for life as we know it. And while we've identified some Earth-sized planets in the habitable zone, we don't yet know if they have water or atmosphere, or whether life exists or could exist on them. But here's the thing that really changes the perspective. We are so small in the grand scale of things. While our Sun is a medium-sized star, it is just one of hundreds of billions of stars in the Milky Way galaxy, which in turn is just one of 2 trillion galaxies in the observable universe. Even our entire galaxy, the Milky Way, which measures about 100,000 light-years across, is just a small speck in the vast cosmic web that stretches out over unimaginable distances. As massive and incomprehensibly large as the Milky Way seems, in the grand scale of the observable universe, it is insignificant. Our galaxy is part of the local group of galaxies, which is a relatively small cluster of about 50 galaxies, including the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Andromeda, the largest galaxy in our local group, contains about 1 trillion stars and measures about 220,000 light-years across. Even though Andromeda is enormous compared to the Milky Way, it is still just a tiny fraction of the overall scale of the universe. The distance between the Milky Way and Andromeda is around 2.5 million light-years, meaning that light takes 2.5 million years to travel from one galaxy to the other. What's truly mind-blowing, however, is that the local group of galaxies, including the Milky Way and Andromeda, is part of an even larger structure known as a supercluster. The Laniakea supercluster, which contains the Milky Way, spans across 520 million light-years and contains about 100,000 galaxies. Laniakea is just one of the many superclusters scattered throughout the observable universe. And beyond Laniakea, there are even larger structures, including the Shapley supercluster, which holds more than 8,000 galaxies. The Shapley supercluster, which is about 650 million light-years away, is one of the largest known concentrations of matter in the universe. But even these superclusters are just a small part of something even more extraordinary, the cosmic web. The universe's matter is organized into a vast network of filaments, clusters, and superclusters, which form a web-like structure that stretches across the observable universe. These filaments are composed mostly of dark matter, which we cannot see directly, but its gravitational influence is enough to reveal the structure of the universe. These filaments are the highways that galaxies travel along, and the nodes where they meet are the massive galaxy clusters. The structure of the cosmic web reveals an important fact about the universe. Matter is not evenly distributed. Instead, the universe is marked by large voids, regions of space that contain very few galaxies, like the Boötes void, a vast emptiness that spans about 330 million light-years. These voids exist because gravitational forces have pulled matter together into the dense filaments and clusters, leaving massive empty spaces in between. As we zoom out and look at the universe as a whole, we can see the incredible scale of this structure. But as we reach further and further into the depths of the universe, we also encounter limits. Limits to how much we can observe, limits to how much we can understand. The observable universe is not the entire universe. It's simply the portion of the universe that light has had time to reach us from, and beyond that, we have no way of knowing what exists. And yet, even within the observable universe, the questions remain profound. How did all of this come to be? How did the universe evolve from the Big Bang to what we see now? And what does the future hold for this vast, expanding cosmos? As we continue our exploration, we now face the deep existential question that has intrigued humanity for centuries. How did it all begin? We know that the universe is 13.8 billion years old, but what does that truly mean for the universe's origins? The Big Bang Theory is the prevailing explanation of the universe's birth, suggesting that the universe started as an incredibly hot and dense point and has been expanding ever since. But let's take a deeper look into this theory and what it tells us about the earliest moments of the universe. The Big Bang wasn't an explosion in the traditional sense. It wasn't like a bomb going off and expanding outward in all directions. Instead, it refers to a rapid expansion of space itself. Space itself began expanding from an infinitesimally small, hot, and dense state around 13.8 billion years ago. Initially, the universe was composed of energy, and as it expanded and cooled, that energy began converting into matter, forming the basic building blocks of atoms. In the first few minutes after the Big Bang, nuclear fusion created the simplest elements: hydrogen, helium, and traces of lithium. These elements formed the first atoms, which eventually clumped together due to gravity to form the first stars and galaxies. But there's something deeply fascinating about this early period. It was a time of pure chaos. The universe was so hot that matter couldn't even hold together. Photons, the particles of light, were constantly scattering off electrons, preventing the universe from being transparent. This era, known as the recombination era, lasted for about 380,000 years, and during this time the universe was opaque. When the universe finally cooled enough for atoms to form, photons were able to travel freely, marking the universe's first moments of transparency. These cosmic photons that traveled freely through space are still with us today, albeit stretched to the microwave part of the spectrum by the expansion of the universe. This glow, called the cosmic microwave background radiation, CMB, is one of the key pieces of evidence we have for the Big Bang. The CMB serves as a snapshot of the universe at the time it first became transparent, essentially providing us with a picture of the universe when it was only 380,000 years old. After the Big Bang, the universe continued to expand, but it also went through periods of cosmic inflation, a period of incredibly rapid expansion that occurred within the first fraction of a second of the universe's existence. During inflation, space expanded exponentially, and the universe went from a size smaller than an atom to a size larger than the entire observable universe in just a tiny fraction of time. This rapid expansion smoothed out the irregularities in the universe, setting the stage for the more structured distribution of galaxies and matter we see today. But understanding the Big Bang is just one piece of the puzzle. As we begin to zoom out and think about the future of the universe, we encounter even more profound questions. Where is the universe headed? Will it expand forever? Will it eventually collapse? Or is there another fate in store for this ever-expanding universe? For much of the 20th century, scientists believed that the expansion of the universe would eventually slow down due to the gravitational pull of matter. This led to the idea that the universe might eventually stop expanding and collapse in on itself, a theory known as the Big Crunch. However, in the late 1990s, observations of distant supernovae revealed something surprising. This led to the realization that there was some mysterious force at work, a force that was pushing galaxies apart rather than pulling them together. This force was named dark energy, and it makes up about 68% of the total energy content of the universe. Dark energy is a form of energy that behaves like a repulsive force. Its exact nature remains a mystery, but it is believed to be responsible for the accelerating expansion of the universe. As the universe expands, dark energy increases, causing the rate of expansion to speed up. In the distant future, as dark energy continues to drive the expansion of space, galaxies that are not gravitationally bound to the Milky Way will be carried away, their light redshifted into invisibility, leaving our local group of galaxies isolated from the rest of the universe. But let's not get ahead of ourselves just yet. We've discussed the early stages of the universe's evolution, from the Big Bang to the formation of atoms and galaxies, and now we must take a step back to consider a larger question. How will this all end? Based on our current understanding of cosmology, the ultimate fate of the universe is tied to the interplay between dark energy, dark matter, and the rate of expansion. The universe's future is closely linked to a process called heat death. This theory suggests that as the universe continues to expand, stars will burn out, galaxies will drift apart, and eventually the universe will reach a state of maximum entropy, essentially a state where all energy is evenly distributed and no more work can be done. As stars die and matter decays, the universe will grow colder, and eventually it will be filled with only the faintest traces of radiation. This is the point at which the universe will enter its dark era, when it is no longer capable of sustaining any life or complex structures. While this may sound bleak, it's important to remember that this process will take place over 1 trillion years. For us, the heat death of the universe is a distant future, so distant that it's difficult for us to even comprehend. But it is, as far as we can tell, the most likely fate of the universe based on our current models. However, not all cosmologists are convinced that heat death is the final answer. There are still alternative theories about the universe's future that haven't been completely ruled out. Some believe that the universe could eventually undergo a big rip, where the expansion of space accelerates to such a degree that galaxies, stars, planets, and even atoms are torn apart. Others propose the possibility of a big bounce, in which the universe might collapse in on itself, only to start the cycle of expansion and contraction over again. The nature of dark energy, which drives the accelerating expansion of the universe, remains one of the most profound mysteries in modern cosmology. We don't yet fully understand what it is, how it works, or what its true effects will be on the universe in the long run. As our understanding of dark energy evolves, so too will our predictions for the universe's ultimate fate. As we move forward in our cosmic journey, we must confront one undeniable truth. The universe is constantly changing. From the Big Bang to the present day, it has been in a state of dynamic flux, and that change is ongoing. Whether the future of the universe will be dominated by the forces of dark energy, dark matter, or something yet undiscovered, we can't say for certain. But the exploration of these forces and their consequences is at the heart of modern cosmology. In the end, we find ourselves standing on the edge of an ever-expanding universe, trying to grasp its scale, its future, and our place within it. But for now, the universe is vast, complex, and filled with mysteries that continue to inspire awe and wonder in those of us who look up at the stars. As we move even further into the cosmos, our next step is to address one of the most mind-boggling concepts in the universe: the infinite scale of space and time. When we talk about infinity, we aren't just referring to something large, but something beyond anything that we can even truly comprehend. The concept of infinity, whether it's in terms of distance, time, or even possibilities, pushes the boundaries of our imagination and understanding. In many ways, we are not prepared for the vastness of what infinity truly means. We often think of it in simple terms: an endless number, an endless stretch of time. But the reality of infinity, in the context of the universe, is far more profound and complex. Let's first consider the universe itself. As we've already seen, The observable universe spans an astonishing 93 billion light-years across. This is already a size beyond any human scale of understanding. But this is just the observable universe. What lies beyond what we can see is unknown, and in fact, it might be far greater than what we can currently measure. If the universe is truly infinite, then it extends forever in every direction, without a beginning or an end. There is no edge, no boundary, no limit to how far the universe stretches. This suggests that the total amount of space in the universe is so large it's incomprehensible. What does infinity mean in terms of distance? Imagine standing at the center of a vast, empty void. No matter how far you travel, you'll never reach an edge because the space you're in is limitless. There will always be more to explore, and the further you go, the further away the end becomes. Even if you could move at the speed of light, you would never reach the end because it simply doesn't exist. And yet, as mind-bending as it seems, this infinity of space has been part of the universe from the very beginning, right from the moment of the Big Bang. Let's zoom out a bit. From our perspective on Earth, we're used to distances that seem large. A drive across a country takes days, and a trip to another continent takes hours. But when we consider distances on a galactic scale, everything changes. The nearest star to us, Proxima Centauri, is about 4.24 light years away. That's about 40 trillion kilometers, a distance so vast that even traveling at the speed of light, it would still take over 4 years to get there. And this is just one star. The universe contains hundreds of billions of stars in the Milky Way alone, and there are billions of other galaxies out there, each containing hundreds of billions of stars as well. The distances between these galaxies are incomprehensible. The nearest large galaxy to us, Andromeda, is about 2.5 million light-years away. A journey to Andromeda at the speed of light would take 2.5 million years. It's impossible to even grasp what this really means, but when you try, it can feel like staring into an endless abyss. The scale of the universe forces us to confront the true meaning of infinity. In a sense, every direction you look is infinite, stretching out into the unknown. We see distant stars and galaxies, but no matter how far we look, there is always more to see. More galaxies, more stars, more distant regions of space that are beyond our reach. And the more we explore, the more we realize that this infinite expanse extends far beyond the edge of what we can observe. Now, let's move to another aspect of infinity that is just as perplexing: time. Time, much like space, is often treated as a linear progression. We move forward from the past, through the present, and into the future. But when you step back and look at the universe on the scale of billions of years, time becomes something else entirely. The universe itself is about 13.8 billion years old, which in human terms is an unfathomable stretch of time. But to the universe, 13.8 billion years is just a fleeting moment in the grand scheme of things. After all, the universe is forever old. It didn't start at a specific point in time, and it won't end at any definite moment. If we look at the future of the universe, we see a different kind of infinity, the possibility that it will continue expanding for an almost unimaginable period, perhaps for trillions of years. Eventually, all stars will burn out, galaxies will drift apart, and the universe will enter a state of maximum entropy, where nothing happens and everything will be cold and dark. This is known as the heat death of the universe, a state in which time itself will be meaningless because all processes will have come to an end. Yet, even though time and space might feel infinite, there are paradoxical elements to the concept of infinity that challenge our understanding. For example, if the universe is infinite in size, that suggests an infinite number of possibilities, but this also leads to some strange conclusions, one of which involves the idea that in an infinite universe, everything that can happen will happen. Take this idea to its extreme. In an infinite universe, there would be infinite copies of Earth, of you, of everything. These copies would be distributed across the cosmos, separated by vast distances. Some of these copies would be nearly identical to you, while others would differ in minor ways, like the color of your shirt or the decisions you made throughout your life. The further you stretch the idea of infinity, the more the boundaries between reality and possibility blur. It becomes clear that in the realm of infinity, reality is not just about what is, but also about what could have been, an endless series of parallel universes where every possible outcome plays out. But here's the twist: we can never reach these other versions of reality. While an infinite universe may contain infinite versions of Earth and infinite versions of you, these versions would exist in different realms, separated by what we call the cosmic horizon. This boundary marks the limit of what we can observe or ever interact with. In a sense, even though infinity holds endless possibilities, it also creates an impossibility. The vastness of space and time means that no matter how much we might want to interact with these parallel versions of reality, we're forever separated from them by distances we will never cross. And while we are limited in our ability to directly perceive infinity, it still shapes our existence. We may never physically reach the edges of the universe or touch an alternate version of ourselves, but the concept of infinity forces us to confront the limitations of our knowledge. It challenges us to think about our place in the cosmos, not just as inhabitants of Earth, but as conscious beings trying to understand an incomprehensibly vast universe. Yet, within all of this infinity lies a paradox that gives us meaning. We are finite beings in an infinite cosmos. And yet, within our brief span of existence, we have the extraordinary ability to understand and contemplate that very infinity. The paradox is what makes our ability to comprehend the universe so remarkable. As we consider the vast expanse of the universe, both spatially and temporally, we realize that there is no definitive, the journey of discovery never ends, and the search for meaning within this infinite expanse is perhaps the most profound pursuit we can Continuing our journey into the infinite vastness of the cosmos, we now turn our attention to the largest structures in the universe. These structures are not just vast in scale, they challenge our understanding of how the universe operates, and they make us question our fundamental assumptions about space, time, and the very nature of reality. We've already touched on the superclusters, enormous regions of the universe containing vast numbers of galaxies. These structures are so large that they push the boundaries of what we thought was possible. But there's a new level to this, an even more complex, interconnected web of matter in the universe that is truly staggering. The largest structures in the observable universe are the filaments and walls of galaxies. These structures, sometimes called the cosmic web, stretch across hundreds of millions or even billions of light years. They are not random. They are the natural result of the forces that govern the universe, primarily gravity. As we move further and further into the cosmos, the universe reveals itself as a vast, interconnected web where galaxies, clusters of galaxies, and superclusters are bound together by the invisible threads of dark matter. Let's start with the largest of these cosmic structures, the Hercules Corona Borealis, Great Wall. This superstructure is the largest known structure in the universe. It spans a mind-boggling 10 billion light-years, more than 10% of the entire observable universe. The sheer size of this wall makes it one of the most perplexing cosmic phenomena. It's so vast that it challenges the current models of how the universe should be structured. According to the cosmological principle, which suggests that the universe should appear roughly the same in all directions on large scales, we shouldn't see something this large. The existence of the Hercules Corona Borealis Great Wall is a profound mystery. Its size forces cosmologists to re-examine everything they know about the distribution of matter in the universe. Either our models are incomplete, or there's something more profound happening at the largest scales that we don't yet understand. What's even more perplexing is that structures of this size shouldn't exist according to our current understanding of the Big Bang and cosmic evolution. The fact that such large-scale structures could have formed in the relatively short time since the Big Bang presents a significant challenge to cosmology. How did gravity manage to pull together matter on such a vast scale in such a short period of time? This question remains open, and it hints at gaps in our understanding of cosmic formation. As if that weren't enough, this Great Wall is not a solitary feature. There are other, Similar structures strewn across the cosmos, each of them massive and full of mystery. One example is the Sloan Great Wall, discovered in 2003, which stretches across about 1.37 billion light years. It's made up of thousands of galaxies, all connected by the web of dark matter. Even though this wall is only a fraction of the size of the Hercules Corona Borealis Great Wall, it is still enormous by any measure. These filaments and walls are not just interesting because of their size, they also reveal the way the universe is structured. Galaxies and galaxy clusters are not scattered randomly across space, they are connected in intricate patterns by the forces of gravity. These threads, these filaments of galaxies, are what make up the cosmic web. The filaments themselves contain mostly dark matter, the unseen mysterious substance that doesn't interact with light but is detectable by its gravitational effects. The galaxies we see are just the markers, the bright points in the dark matter web, like cities scattered along a highway. Between these cosmic filaments, we find what are called voids, vast empty regions of space that contain very few galaxies. These voids are the largest unfilled spaces in the universe. The most famous of these is the Berkeley Void, a roughly spherical region of space about 330 million light-years across, with very few galaxies inside. These voids are not completely empty. They contain some gas and dark matter, but the density of galaxies is extremely low. When you're inside one of these voids, you are surrounded by near silence in the universe. There are no galaxies, no stars, no superclusters. The voids give us a profound sense of how empty the universe can be, despite all the vast structures we've talked about. One interesting aspect of these voids is that they are not entirely devoid of anything. As we've learned, they still contain dark matter and gas, but the concentration of galaxies is so low that they appear empty. These voids are the result of the same gravitational forces that create filaments and walls, but instead of clumping together, the matter in these regions has been stretched thin. It's almost as though the gravitational vacuum created by the mass of the filaments pulls the galaxies out of the voids, creating enormous empty spaces. It's almost like the universe's version of a bubble, structure formed by forces that we can't yet fully understand. These vast structures, filaments, walls, and voids, are not just an abstract concept, they are the building blocks of the large-scale structure of the universe. They are the result of gravitational instability in the early universe, as tiny density fluctuations were amplified by gravity over billions of years. These structures are the cosmic equivalent of the webbing of a spider's web, delicate, intricate, and spread across unimaginable distances. And just like a spider's web, they are constantly evolving. The forces of gravity continue to shape them, pulling more and more galaxies into the filaments, adding more matter to the voids, and continuing the cycle of cosmic evolution. The cosmic web is the most profound representation of how the universe is interconnected. It's a network, a lattice of galaxies and dark matter stretching across unimaginable distances. And it's a reminder that even the most distant galaxies, the most isolated stars, are all part of this grand structure. No matter how far away we look, we are all connected by this gravitational web. But what happens when we zoom out even further? What happens when we consider not just our observable universe, but the entire universe? The part that stretches beyond what we can see, beyond the cosmic horizon. This is the next question we must confront, and while we may not yet have the answers, understanding the large-scale structures that make up the observable universe is crucial to understanding the true scale of the cosmos. As we step back to take in the full picture of the universe's grand design, we begin to realize how truly unimaginable the universe is. The structures we see, whether they are the cosmic walls, filaments, or voids, are just the beginning. They are like the first steps on a journey that will take us far beyond what we can currently grasp. As we move forward on our cosmic journey, it's time to zoom out even further past the local galaxies, clusters, and superclusters. The scale of the universe is mind-boggling. But what lies beyond what we can observe? How do we even begin to understand the true size of the universe, let alone the unimaginable structures that lie hidden beyond the limits of our telescopes? To comprehend what lies beyond the observable universe, we first need to understand the concept of the cosmic horizon. The cosmic horizon marks the boundary beyond which we can no longer see or detect anything. It's defined by the maximum distance that light could have traveled since the beginning of the universe. This is a fundamental limit to our observations, because light travels at a finite speed, and as the universe has expanded, the light from distant galaxies has been stretched, redshifted, and lost beyond our reach. But even within the observable universe, the distances are so vast that they are difficult to grasp. Let's try to understand this concept in a tangible way. Imagine the observable universe as a giant sphere with a radius of about 46.5 billion light years. That means the entire observable universe is about 93 billion light years across, a number that's almost impossible to comprehend. But here's the catch. The universe itself is much larger than the observable universe. In fact, it's almost certainly infinite. The observable universe is just the part we can see and measure, constrained by the speed of light and the expansion of space. The light from objects beyond the cosmic horizon simply hasn't had time to reach us yet. This means that the universe is far larger than what we can detect. If we had an infinitely powerful telescope, we could potentially observe galaxies, stars, and other structures that are so far away that their light has been traveling for billions of years, and some of these objects may never reach us at all. In fact, the true size of the universe, the part beyond what we can see, remains one of the greatest mysteries of cosmology. It's often said that the universe could be infinite, but how do we prove something like that? How can we be certain that the universe doesn't extend forever in all directions without any boundaries? One theory that has been proposed to explain the vastness of the universe is the idea of eternal inflation. According to this theory, our universe began as a tiny point, an infinitely small singularity, before expanding rapidly in an event known as inflation. This expansion was faster than the speed of light, meaning that different regions of the universe became disconnected from each other. This process, known as eternal inflation, suggests that new universes are constantly being created, each one expanding at its own rate. Our universe is just one bubble in this infinite sea of universes, each with its own set of physical laws and constants. If the universe is infinite, then there are likely an infinite number of galaxies, stars, and planets beyond the cosmic horizon. The observable universe, while vast beyond measure, might just be a small portion of a universe that continues infinitely in all directions. There may be countless galaxies, each with billions of stars and potentially habitable planets, scattered throughout the universe, but we'll never be able to observe them because they are beyond our reach. The idea of an infinite universe is hard to comprehend, yet it might be the simplest explanation for the immense scale of the cosmos. And what's even more fascinating is that this concept extends beyond just space. It includes time as well. In an infinite universe, time could also extend infinitely in the future and the past. The history of the universe could be an eternal cycle, with new universes being born while others fade away. But beyond the size of the observable universe and its potential for infinite growth, there is the still unsolved mystery of dark matter and dark energy. As we have discussed before, dark matter makes up about 27% of the universe's total mass energy content, but we still have little understanding of what it is or how it behaves. Dark energy, even more elusive, accounts for 68% of the universe's energy, and it seems to be driving the accelerating expansion of the universe. Could dark matter and dark energy be the keys to understanding the true scale of the universe? Are they related to the structure and growth of the universe in ways we don't yet understand? Some researchers believe that dark matter and dark energy may play a critical role in the formation of the largest cosmic structures. If they are indeed responsible for the cosmic web, the filaments, walls, and voids we see in the universe, then understanding their properties could unlock the next great frontier in cosmology. The sheer amount of dark matter and dark energy in the universe is astonishing. They account for 95% of the total content of the universe, yet we can't see them or directly interact with them. This is a major puzzle for scientists. The vast majority of the universe's contents are invisible, and they seem to be completely out of our reach. What does this mean for our understanding of reality itself? This brings us to a crucial question. How do we even begin to understand something so vast, so distant, and so intangible? Our best tool in this quest is the scientific method. We rely on observation, experimentation, and theory to build models of the universe that help us explain what we see. But these models are always limited by the data we can collect and the tools we have at our disposal. As our tools improve, so too does our understanding. New telescopes, such as the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, are allowing us to peer deeper into the cosmos, beyond what was once possible. These instruments are already providing us with more detailed images of distant galaxies, stars, and exoplanets than ever before. With this new data, we can begin to refine our models and build a more accurate picture of the universe. But despite our best efforts, the universe will always remain vast, mysterious, and beyond our full comprehension. There will always be new frontiers to explore, new questions to ask, and new discoveries to be made. And that is what makes the study of the universe so exciting and endless. As we continue to explore the infinite vastness of space, we are reminded of just how small we are in comparison. The universe is so large that it defies our ability to truly grasp its scale. Yet, in our pursuit of knowledge, we have managed to understand so much about it. The quest to understand the universe is a journey that will never end, because as soon as we learn one thing, we are faced with even more questions. So, what's next? As we dive deeper into our understanding of the universe, we will explore the intricate cosmic structures, the forces at play, and the mysteries that remain unsolved. We'll continue to push the boundaries of our knowledge and get closer to uncovering the secrets of the dark universe. A universe that, though vast and incomprehensible, continues to beckon us forward. In our last discussion, we explored the incomprehensibly vast nature of the universe and its likely infinite scale. But there's something even more intriguing that lies beneath the surface. The structures that emerge from this cosmic fabric, often hidden from our view, yet shaping the universe we see today. As we continue to zoom out, what do these structures reveal about the universe? And how do we make sense of the patterns, the webs, and the dark, invisible forces that govern it all? Now let's look at the largest structures in the universe. When we map out the galaxies in our observable universe, what we find isn't just a random scattering of points. No, what we find is a vast cosmic web. This web consists of filaments, voids, and clusters of galaxies, all interconnected by gravity in a complex, almost elegant dance of matter and energy. It's not just random, it's an organized pattern that has taken billions of years to form. The cosmic web is the result of gravitational instability, the process by which small variations in the density of matter in the early universe were amplified over time by gravity. These variations eventually led to the formation of galaxies, clusters, and superclusters of galaxies, massive structures that stretch across billions of light years of space. One of the most remarkable features of this cosmic web is its scale. The filaments are essentially long strands of galaxies stretching across vast stretches of space, connecting clusters and superclusters like pearls on a necklace. In between these filaments lie vast voids, enormous bubbles of empty space where galaxies are almost entirely absent. These voids may seem empty, but they are a key feature of the structure of the universe. In fact, these filaments and voids together form a structure that looks like a giant sponge. Imagine a foam with galaxies clustered along the edges of bubbles, separated by vast stretches of almost empty space. This is the true large-scale structure of the universe. These structures, these cosmic sheets, are incredibly large. Some of them stretch across billions of light years, yet they are still just the visible part of a universe that likely extends infinitely beyond our reach. One of the largest structures we've discovered is the Sloan Great Wall. This massive cosmic filament stretches an incredible 1.37 billion light-years across, making it one of the largest known structures in the observable universe. It's not a single entity, but a vast network of galaxies connected by gravity, with a structure so immense it challenges our understanding of how such vast formations can exist in such a short period after the Big Bang. But even this pale in comparison to the Hercules Corona Borealis Great Wall, which may span a staggering 10 billion light-years. This is so large that it constitutes more than 10% of the observable universe. It's a structure so massive that it could fundamentally challenge our cosmological models, particularly the cosmological principle that suggests that the universe should look roughly the same in all directions and on large scales. What does the existence of such enormous structures mean for our understanding of the universe? Well, for one, it suggests that gravity has played an even more dominant role in the formation of the universe than we thought. These massive structures have formed over billions of years, with dark matter playing a crucial role. The dark matter we cannot see forms the underlying scaffolding for these galactic filaments, providing the necessary gravitational pull to attract regular matter and allow galaxies to form. However, as vast as these structures are, they only represent a fraction of the universe's true scale. The rest, the part that remains hidden, is even more mysterious. There's still so much we don't know about what lies beyond our cosmic horizon, the boundary beyond which no light can reach us. The light from galaxies far beyond that point has simply not had enough time to travel to Earth. These galaxies are effectively invisible to us, and yet they make up a significant portion of the universe. As we look deeper into the heart of the cosmic web, we encounter some truly mind-bending phenomena. For instance, some galaxies in the far reaches of the universe seem to be moving away from us at speeds faster than the speed of light. This is not a violation of the laws of physics, because it's not the galaxies themselves moving faster than light. Rather, it's the space between us and those galaxies expanding at such a rate that their light is stretched to the point where it becomes undetectable. This expansion of space itself is driven by dark energy, a mysterious force that is causing the accelerated expansion of the universe. We've mentioned dark energy before, but it bears repeating here. Dark energy is thought to make up about 68% of the total energy in the universe, and yet we still don't fully understand what it is or how it works. All we know is that it is driving the universe apart, stretching the distances between galaxies, and pushing us farther and farther away from regions of space that once might have been within our reach. Despite the overwhelming force of dark energy, gravity still has the final say. The cosmic web, while expanding at an accelerating rate, is still held together by gravity. This is why galaxy clusters, superclusters, and even the larger walls of galaxies remain intact. Gravity is strong enough to bind these structures together despite the expansion of the universe. But what about the voids? These massive regions of empty space represent the largest and most perplexing feature of the cosmic web. The voids are vast expanses where no galaxies or very few galaxies exist. These voids stretch for hundreds of millions of light years, and they can contain billions of light years of space with no discernible objects. Yet, despite their emptiness, they play a crucial role in the cosmic structure, influencing the movement and distribution of galaxies within the larger web. Now, while we have made huge strides in understanding the cosmic web and the forces that shape it, there's still so much we don't know. The structure of the universe is likely incomprehensible in its full form. Our observations are limited, not just by the distance of galaxies, but by the limitations of our technology. The fact that we can only observe a small fraction of the universe makes it incredibly difficult to draw concrete conclusions about the universe's ultimate structure. So where do we go from here? Future telescopes, such as the James Webb Space Telescope, are going to push the boundaries of our understanding even further. By peering deeper into the universe than ever before, these telescopes will allow us to observe galaxies that formed only hundreds of millions of years after the Big Bang. They will provide us with glimpses of the early universe, allowing us to better understand how the first stars and galaxies formed and how the cosmic web came into existence. Even though we've mapped out the structure of the observable universe, we're still very far from understanding its full scale. The fact that the observable universe is likely just a tiny fraction of what actually exists means that there is so much more out there waiting to be discovered. The universe is far more complex and larger than we can possibly imagine. As we conclude this part of our journey, we're reminded of just how small we are in the grand scheme of things, but at the same time, we're reminded of how significant our understanding of the universe is. Despite the vastness of space, we are capable of understanding it, piece by piece, galaxy by galaxy, filament by filament. And that is what makes the pursuit of knowledge so powerful. It's a never-ending journey, one that leads us ever deeper into the cosmos. As we reach the final stretch of our journey, it's time to zoom out once again. We've seen how the universe is structured, how galaxies are woven into a grand cosmic web, and how dark energy and gravity govern the fate of galaxies. But the ultimate question remains: what is the future of the universe? What will happen when the stars burn out and the galaxies drift apart? Is there an end, or will the universe continue to stretch forever? Let's begin with star formation. Right now, in galaxies across the universe, new stars are being born in nebulae, vast clouds of gas and dust. However, star formation is not an eternal process. The raw materials for creating new stars are finite. Every time a star forms, it uses up the gas that could be used for future stars. Over time, galaxies will run out of gas, and star formation will slow down. Eventually, it will cease altogether. As star formation declines, the universe will enter its final stages. The degenerate era is what awaits the universe in the far future, when star formation has come to a halt. The stars that remain will gradually burn out, and only remnants like white dwarfs, neutron stars, and black holes will remain. In this era, the universe will grow darker and colder as the remaining stars fade away, and the universe will become a place of starless voids. But even these stellar remnants won't last forever. Black holes, those enigmatic regions of space with gravitational pull so strong that nothing, no matter, no energy, can escape, will be the last survivors of this cosmic decay. Over unimaginable stretches of time, they will eventually evaporate, thanks to Hawking radiation, a process by which black holes lose mass and energy. The largest black holes, which might have been born from the collapse of supermassive stars, could take trillions of years to evaporate completely. Even the most massive black holes will eventually fade away, leaving behind nothing but the faintest remnants of their once immense power. But this process doesn't happen overnight. In fact, the heat death of the universe, a time when all matter will have decayed into diffuse radiation, is still trillions of years away. For now, stars continue to shine, and galaxies continue their slow dance across the vast expanse of space. But we are living in the midst of a cosmic transition, a transition from a time of active star formation to one where the universe cools and fades into a dark, lifeless void. While the death of the universe might seem like a depressing thought, it's not all bleak. In fact, the universe's ultimate fate, its heat death, marks the culmination of a journey that began 13.8 billion years ago with the Big Bang. Over billions of years, life arose on Earth, consciousness emerged, and the universe began to understand itself. The very fact that we are able to study the universe, to contemplate its vastness and its future, is a testament to how incredible our existence is in this infinitesimal moment in time. But there's still so much to explore, and even as the universe's future unfolds, we continue to advance our understanding. We have already made breakthroughs in our understanding of space and time, from general relativity to the discovery of gravitational waves. Our ability to observe distant galaxies, the cosmic microwave background radiation, and the elusive nature of dark matter is giving us new insight into the structure and evolution of the universe. And who knows what future discoveries will further reveal the universe's secrets. Yet, with each new discovery, we are also reminded of the impermanence of everything around us. The galaxies we observe, the stars we gaze at, and even the Earth we call home, are all temporary. Everything is changing, evolving, and eventually fading away, whether through the expansion of the universe, the slow decay of stars, or the eventual evaporation of black holes. But it is precisely this impermanence that makes the search for knowledge so important. We may never fully understand everything, but every step we take toward greater understanding adds meaning to our brief existence. As the universe itself becomes ever colder and more distant, we, as conscious beings, can reflect on the incredible journey that brought us here, the emergence of life, the rise of civilization, and our ongoing quest to explore the cosmos. The universe is vast, and our place in it is both humbling and inspiring. Though our individual lives are small in the grand scheme of things, our ability to grasp the enormity of space, time, and existence makes us significant in ways we cannot fully comprehend. As we reach the end of our journey through the universe's scale, we're reminded of how precious our time is here and now. Thank you for joining me on this journey through the universe. We've touched on just a small fraction of the incredible story that surrounds us. As the universe continues to evolve, so too does our understanding of it. This journey is far from over, and who knows what wonders we'll discover next. Keep looking up, because the universe is full of mysteries yet to be uncovered. Thank you for watching. If you enjoyed this exploration of the cosmos, don't forget to like the video and subscribe for more incredible content.